Okay, that worked. Okay, everyone. Thanks. We'll maybe get started. Thanks, everybody, for coming. It's my great pleasure to introduce Erica, who's come back from Penn State in the US to present the seminar today and get back in touch with people, friends, family, and other. And she's here on Big Questions Institute Fellowship. She was granted some funds to promote early career researchers doing exciting research on the big questions of science. The BQI used to be here at UNSW, but now it's an independent organization that is out to promote science and also to foster early career on some of the fundamental research, big questions of science. So we both thank the BQI for that. Erica, as most of you would know, was a grad here. She finished her PhD in 2019 on a suite of microfossils from rocks that are right at the transition from early Earth to modern Earth, and she was able to document a more complex variety of microfossils, including, I think, 3 types previously unknown to science. And she's still in the process of writing that up. And on the strength of that work, she got accepted as a NASA postdoctoral fellow at Penn State University in the Laboratory for Agnostic Biosignatures under the leadership of Chris House. Now, agnostic biosignatures is really what works into the title that Erica's got here, looking for life as we don't know it. And so Erica will really explain that. It's a pretty new concept. And really, you've been in, I think the starting is pretty timely, isn't it? You're really at the beginning of this kind of research. And so, yeah, we're very excited. Thank you for coming back and giving us this talk, and lovely to hear from you.
Thanks for the introduction. Still trying to admit people that into the room on the online. All right, So as many of you know, astrobiology is the study of the origin, the evolution, and in theory, the distribution of life in our universe. And it encompasses many different disciplines: chemistry, physics, geology, astronomy. And although these are quite wide disciplines, they're actually tied together by one ultimate question: are we alone in the universe? And there are many ways to go about trying to answer this question, from chemists studying the origin of life to try and figure out the environments of where life may have arisen elsewhere, to geobiologists investigating the history of life on Earth and the types of environments that it inhabited, so that we can find out what types of environments to look elsewhere, to planetary scientists looking for habitable environments on other planets, and to astronomers looking for rocky planets within the Goldilocks zone, where there might be liquid water at or near the surface. So the information gathered from one discipline is actually critical to the others. So we need to know how life originated and in what environments it originated in order to actually look for it elsewhere. So that's the interdisciplinary nature of astrobiology, and that's a really great thing. The one thing I really love about astrobiology is it's connecting all of these disciplines, and I can see from the people in the audience today, it's actually a good representation of these different disciplines. So the thing that connects all of this so far is that it's based on life as we know it here on Earth. And that's a really great way to go about answering the question of are we alone in the universe, because it's logical. It's looking at life as we know it, the sample size of 1 here on Earth, and then taking that and extrapolating it to search elsewhere. But as we extend this search for life further out into our solar system to places like Europa or Titan, or even further beyond, these worlds are really strange and different And we have to consider whether these worlds might actually harbour life, assuming they harbour life at all, whether they harbour life as we know it or something else entirely, something completely different. So the question is, would we actually recognise life if we were to come across it elsewhere? So to address this, we really need to come up with characteristics that might represent universal features of life so that we can avoid or at least reduce the likelihood of false negatives for life detection, as in dismissing something as non-life when it actually is life. And this concept is the reason behind the formation of the Laboratory for Agnostic Biosignatures, or LAB for short. LAB aims to develop tools and methods for life detection that encompass a wider definition of life to give us this greater chance of recognising life were we to come across it elsewhere. And essentially, an agnostic biosignature just means something that isn't tied to a particular metabolism or characteristic of life as we know it. So research at LAB is currently centred around 4 main themes: molecular complexity, chemical fractionation or elemental accumulation, energy disequilibrium or energy transfer, and molecular complementarity, which can also be thought of as surface complexity. So I'm going to go through a few of these with some examples. So one way to look at molecular complexity is to think about how molecules are actually assembled. So the idea here is that there's a certain threshold at which molecules become too large and complex to have formed in the absence of life. So when they're very simple, they can be formed in many different ways, both life and non-life, but once you reach a certain threshold indicated by the red bar, it actually gets too complex and can only be formed by life. So that's one way to think about molecular complexity. And a recent paper by Marshall et al. Last year developed a way to actually measure molecular complexity using what they called molecular assembly theory, or MA theory. And basically, this theory can be used to indicate the number of steps required. Sorry, can you see? The number of steps required to construct a molecule. So as you can see here, the number of parts increase with each step, and each step is given a molecular assembly score. But you'll notice here between 3 and 4, they're not just adding one more digit, they're actually using a pre-assembled kind of step and replicating it and adding one more. So it's basically what's the simplest number of steps you can use to create a molecule, and that's the score, this molecular assembly score that they made. So this group looked at a range of different materials and scored each one of them using this theory and compared them in this graph here. So as you can see, there's the color code on the right: abiotic, biological, dead, blinded, and inorganic materials, and they're all graphed together. But what I want to point out here is that they actually figured out that the threshold is a molecular assembly score of 15. So 15 or above is the threshold where molecules become too large and complex and that they're only produced by life. So just to delve in a little bit more to the background data behind this, each of the materials are listed along the bottom, and you can see it's the same color code as the graph in the center. And they looked at a range of biological materials in green. You'll see they have quite high scores. Dead biological materials is blue, so heated yeasts and coal. Going across again to the orange, there's rocks and minerals that they tested or analysed. And then the blinded materials were used as a kind of test to see where they actually fit in the system. And the thing that I find extra interesting is the very far right one, mid-Miocene paleomat. This sample is a sediment sample from a lake bed that's 14 million years old. And so it's still sediment. And they did this molecular assembly score analysis on it, and it hit well into the biological range. So it shows that even something that's, I mean, it's not quite fossilized, but it's pretty old, that this method still works for it. So Another interesting thing to come out of this is that this method actually allows one to search for what life does rather than needing to define what life is, because defining life is quite complex in itself. So it's a kind of, yeah, pretty cool way to try and tackle this agnostic viewpoint. And another kind of arm of the Laboratory for Agnostic Biosignatures is chemical fractionation. And there's a number of ways to think about this, but I'm just going to go into two here: elemental stoichiometry and elemental accumulation. So firstly, with the stoichiometry, there's work being done looking at what's called the Redfield ratio and trying to think about how this can be an agnostic biosignature. So the Redfield ratio is the ratio of carbon to nitrogen to phosphorus of biomass in our oceans. And worldwide, everywhere, pretty much everywhere this has been measured on the globe, it's this consistent ratio of 106 to 16 to 1. So yeah, it really underpins our knowledge of the nutrient cycling in the oceans. So this group looked at the Redfield ratio, and although it holds true broadly speaking, when you look at it in a bit more depth, there's actually nuance there. So they found that this is the Redfield ratio in the dashed straight line, and their data is in the curve. They found, as you can see by the graph, that it varies slightly. And so they used this data to say that, well, as cell volume increases or varies, sorry, the stoichiometric ratios vary alongside the cell volume. So an agnostic biosignature in this kind of framework is that a ratio changing systematically with varying size could be an indicator of a universal sign of life. So now looking at elemental accumulation, the idea behind this is that through metabolic processes, life utilizes, concentrates elements, and so these could be actually highlighted using different techniques visually, like shown here. So there's the three images, the same cell, and you can see carbon and nitrogen in the top, phosphorus, and then copper. So this is a clear regular biosignature, but extrapolating on this from an agnostic viewpoint is if there was a really distinct concentration of elements different to the localized surrounding environment, that could be an indicator for life. And especially if this distinct concentration was had some kind of boundary structure or compartment or something to separate it from the outside environment. And energy disequilibrium. So all life needs to transfer energy in order to grow and reproduce. So a way to think about energy disequilibrium as an agnostic biosignature is to look at sites of energy transfer like redox gradients and describe their attributes. As one example, this graph is from a paper that isn't looking at biosignature specifically, but what they found is really applicable. So they looked at mine tailings, so the wastewater from mining, and inside this gooey sludge, the wastewater, there's iron sulfide oxidation happening. And so this happens both abiotically and biotically, or biologically. And so they were able to actually measure both the life and the non-life version of this iron sulfide oxidation. And what they showed was that the life actually produced a really strong current or voltage shown here. So the life is the open triangles, and the non-life or abiotic oxidation is shown by the squares, and it's just quite a subtle little energy current. So they showed that life actually is distinct. It creates this energy gradient. So again, an agnostic biosignature in this context would be looking at redox gradients and finding something that's abnormal from the abiotic background. And this feature in particular would be an indicator of active metabolism. So much of the research effort by labs so far has been directed towards current or extant life, But what about past life? We currently don't actually know what an agnostic sign of past life might look like. And this is an important area to look into because, as probably most of you know, in recent decades especially, there's been a huge investment into searching for signs of past life, most notably on Mars. But all of this has been based on life as we know it, which means we could actually be overlooking signs of life without realizing it. So the Curiosity rover landed back in 2012, and it's still working on the surface to this day, almost 10 years later. It's characterizing the rocks on Mars, looking at the depositional environment, and assessing the potential for the environment to have supported life in the past. The Perseverance rover, which landed last year, is directly looking for signs of past microbial life in the deposit, delta deposits of Jezero Crater. And the Chinese Space Agency's Zhurong rover also landed last year, and it's investigating the geology and the climate history of Mars. And there's also a couple of upcoming missions, the European Space Agency's Rosalind Franklin ExoMars rover, as well as the joint mission by NASA and ESA to hopefully bring back samples from Mars that the Perseverance rover has collected, possibly later this decade, might be next, let's see. Sorry, just admitting someone else to the room. So all of this investment into searching for signs of past life is currently based on the model of life as we know it. And because we don't actually yet know what a past agnostic biosignature might be, we risk not recognizing features of fossilized life were we to actually come across them. So this issue drives my postdoc research, where I'm seeking to uncover characteristics of fossils that might be able to be considered universal features of past life. But before I dive into that, just some background on traditional signs of past life. These biosignatures are fairly well constrained and include physical characteristics such as morphology and texture, and this can be on the macroscopic or the microscopic scale. But it also includes geochemical characteristics, so certain organic molecules, elemental or mineralogical abundance and distribution, and also isotopic fractionation of key elements. So with fossils, it's also important to note the contextual evidence, so the environment of deposition, the taphonomic or degradational effects on the fossil, and also the deformation or metamorphic history that the rock unit's been subject to. So you need to take into account all these features because what's there preserved in the rock might be completely different to what was there in life before it was preserved. So how does one agnosticize all of this? Well, the idea is that there are some features that conceivably would be common to all life regardless of its origin, as all life has to transfer energy and metabolize in order to replicate and reproduce. So this causes interaction between the biological and the physical, or abiological, which leaves behind clues in the rock record that act as markers of the life processes having taken place. And it's these markers that might be considered universal signs of past life. For example, if there are structures in a rock that exhibit a preferred growth orientation compared to the surrounding matrix, this might be in response to light, but doesn't have to be. It could be in response to chemicals or radiation or some other environmental parameter of the world that you're looking at. And these structures would be considered a universal sign of life despite the type of energy used and the type of organisms. So it's kind of a broader way of thinking of a morphological feature. And another potential agnostic biosignature could be if there's an unusual elemental or mineral accumulation that isn't necessarily expected of a particular rock type. And similarly, an unusual isotopic fractionation not explained by known processes. So I started focusing on two of these categories of biosignatures, the morphological/textural and the elemental/mineralogical for my postdoc research, where my main aim is to leverage our knowledge of the traditional biosignatures to try and come up with specific features that might be universal indicators of past life. So this graphic is kind of how I picture it, or started trying to picture it. Knowledge about Earth-centric biological processes are in the top left, grading to abiological processes in the top right, and then life as we don't know it on the bottom left, and strange, unknown abiological processes on the bottom right, and all sorts of combinations in between. But then I realized it's difficult to try and think about life as we don't know it when the abiotic background processes on Earth are often themselves unclear. So before we're able to look at identifying universal signs of life in rocks or anything down in this bottom half, we need to first have a good understanding of what is happening on Earth with the abiological side of things. Because it's only by understanding this abiological background that we can really recognize any outliers that might then be attributable to biology. But again, as it turns out, it's actually quite hard to look at abiology on Earth because life is everywhere. It's super saturated, basically the globe. It's in sediment kilometers under the seafloor. It's in Arctic terrains. It's subsurface in caves and in mine shafts. So it's quite hard to find something that life hasn't impacted on Earth. So this means that when we're using Earth as an analogue, which a lot of us do, it means the question moves from, is there evidence of life here, to has life influenced the formation of what we're looking at? So the way I've tackled this life is everywhere problem is to use rocks from the early Earth, from a time when life was not necessarily saturating every aspect of the environment. So I'm currently working on a study that interrogates the relationship between biotic and abiotic features in 2.4 billion-year-old rocks from the Turi Creek Group in Western Australia. And this unit is really well constrained. We know that it was a carbonate reef environment that may have looked something like this, excluding the mangroves, of course. And this sequence contains both fossiliferous and non-fossiliferous units. And it was only heated during the rock forming process to about 250 degrees, which might sound like a lot to us as humans or even non-geologists, but really in geology that's quite a low temperature, and it means that the fossils are quite well preserved. So I'm looking at 3 sets of carbonate rocks from this locality. The first set are samples that contain features of definitively biological origins, such as this stromatolite fossil shown here. The second set are of mixed origin. So as an example, the one shown here has microbial mat interlaid with sediment. So it's a mixed sample. And then the one on the right is non-biological, like thinly bedded carbonates. So I'm in the process of using a range of in situ spatially resolved analyses to compare the textural, elemental and mineralogical compositions of these 3 sample suites in order to identify features or relationships within these sets that I can specifically categorize as biological and mainly abiological, if we can really tease that out, just so we can improve our knowledge of the abiotic background. So the idea is that because these rocks, this whole entire sample suite comes from the same locality, and this locality is quite well constrained, we know that the rocks have been subject to the same conditions in their history. The underlying assumption from that is that these rocks should essentially be the same, except where they've been influenced or impacted by biology. So we should be able to tease apart these different features. So although I'm in the middle of this research right now, I anticipate that elemental and mineralogical patterns will emerge, maybe the presence or absence of certain minerals or the distribution of particular elements, and that these patterns will be able to be tied directly to either the biological or the abiological samples. And ultimately, this work will better define characteristics of the abiotic background in this system. And down the track, I plan to apply the relationships I find to another rock type from this system. So I'm looking at the moment at carbonates. I then plan to apply the same thing to chert, which is a silica-rich rock and kind of like quartz, and to test whether the things that I find are actually because of the rock type or if they can be actually applied more broadly. And then down the track, I plan to apply those relationships to other deposits from the Earth to see if, to kind of extend this and see if the patterns follow to the other sample suites. And yeah, I guess it can be also applied then to deposits that are less well constrained, to start testing whether the relationships I find might be universal indicators of life or non-life processes. So to start trying to expand out from what we do know. So thank you very much for today, for coming to listen to a bit about the life as we don't know it. And I want to give a really big thank you to the Big Questions Institute for supporting me and enabling me to come out and share this research with you today. Also, Professor Chris House is my advisor at Penn State. So thank you to him and the greater team that he runs. Brendan for some images I used, Shay for some graphics, and the larger Laboratory for Agnostic Biosignatures team. Thank you.
Thanks, Erica. We've got, I think, plenty of time for questions. It's a nice broad introduction to the topic, isn't it? So, somebody got any questions?
Yeah. I was just wondering, when you were talking about, your agnostic biosignatures, the characteristics, the level of molecular complexity that you're seeing on Earth compared to formed by biological life and non-biological life, and your research comparing it on Earth, geological signatures versus biological signatures. How do you translate that into a different world setting where the geological and mineral and compositions, atmospheric, are all going to be very different?
That's a great question. And I think part of that transferability comes from really understanding this abiotic background on Earth, because although life is complex, the abiotic background theoretically there's only so many ways you can do stuff without life. We're using the same elements. You've still got chemical gradients and heat and temperature gradients, and the constraints are still kind of the same. So the idea is that they would be fairly transferable, knowing, once investigating the parameters of that system. Yeah.
Very good talking. I'm really curious with trying to work out the abiotic side, if I was the devil's advocate. You kind of alluded to it earlier about life being literally everywhere, and particularly microbial life. So my question is, on Earth, are you ever going to truly get an abiotic sample? Like, even if it's not a fossilized mat or a stromatolite, it could still have current day microbes, endolithic microbes that have poured in there, and maybe they're going to muddy the waters of your signatures, even if they weren't formed how many million years ago. Like, I'm just wondering how you truly get an abiotic sample.
Also a great question. Yeah, the answer is we can't know for certain, but the idea is that by going back, to the early Earth, there wasn't all this macroscopic life around. It's just minimizing that, reducing that assumption. And in terms of a later thing like endolithic boring, you can distinguish that in rocks. You can, through the Keppel study and the context. So I can't say, for certain that the thinly bedded carbonates weren't influenced by microbes themselves. Like, we're never going to know that, but it's as close as we can get to it. Yeah. Hey.
Hey, amazing talk, Erica. Following up from Brendan's question, I guess, if we look at samples from Mars or images from Mars, that's the best abiotical system that we have, because at the moment we haven't seen any life there. And people, and it's, a similar planet to Earth, and people applying these, rules or systems you're coming up with to what's happening on Mars, or like looking at geology there.
Not that I know of. Doesn't mean it's not happening, but it would be something that I would love to kind of dive into as this progresses. And start applying it to, because there's so much data now generated by Curiosity, and now that Perseverance is online as well, like, there's just going to be, decades worth of sifting through and seeing if that, the things that we're looking at here can be applied to the data that's already collected, let alone future missions. Yeah.
Would you happen to remember on the top of your head how they did the iron sulfide monitoring, like voltage monitoring experiment?
No, but I can give you the paper and you can go into it. Yeah.
Yeah, just curious.
I think it was that they took samples back to the lab and set up from there. They didn't do it in the field or anything.
Yeah, because there's a time on the X coordinate. I wasn't sure how they actually managed to monitor it.
Yeah.
Or like hundreds of hours. So
I can link you the paper. Yeah.
thanks.
I've got a question. Given your experience as a mapping geologist, and I know that was one of the benefits that Penn State saw in you coming as a postdoc, bringing that experience, and being familiar then with the mapping that's going on with Curiosity and Perseverance, you know, that the length of time it takes to sort of sort out the biological and abiological on Earth. How do you feel that the scientific instruments on Mars gives you potential insight to those different end members you talked about, or is that still going to be a challenge, just in terms of like the amount of data that we do have?
I think we need, there's a ton of data, and if there were 50 people with my background, I think it would still take a long time to sift through it all to look at it from that angle. So yeah, I really think it is something I personally could be looking at for the next bunch of years. But yeah, because it's possible, it's having a bit of insight into that now. I'm a collaborator on the Curiosity rover, so I've been involved with the sedimentology and stratigraphy team meetings, and just seeing the rate at which data is collected and the rate at which the rover moves. And it's like, I'm not saying that this is likely, but there could actually be signs of life that we haven't actually been able to sift through and find yet from the data already collected, just because there is so much there. And yeah, so it's kind of an ongoing work in progress. Yeah.
Shall we see if there are any questions online? Should we just check the chat room?
So Christine online, yeah.
My stupid question was because you used moon rocks as an abiotic sample, given that they should be made of much the same stuff as the early Earth would have been made of.
Yeah, so did everyone hear that? Should I read it out? Yeah. Okay, so Christine online says, presumably rocks from the moon could be used as really abiotic sources, but with the same underlying materials in them as the early Earth. That's a really great idea. I guess one way to look at that is, it's about the type of environment as well. So it's about trying to define or quantify abiotic processes in an environment that's conducive to life. So although the moon rocks could be a really good abiotic source, they aren't necessarily a comparable environment where we could expect to find life. I don't know, it's kind of blurring the lines, isn't it? Because it's like, well, you're trying to find life as we don't know it as well, but it's still kind of constrained to a suitable environment in some form, because you still need water and energy, or some fluid and energy source. So something like the moon that wasn't. Just suggesting them as a boundary condition. Yeah, it would be a good, like, one end of the spectrum. Yeah. I think the others are just comments rather than questions. Yeah. Does anyone else have any questions?
I had my hand raised, Erica.
Oh, sorry. I haven't got the view on the top. Was that Steve? Hi, Steve.
Yeah. Hi.
How are you going?
So this sort of maybe follows a little bit from the previous question. And it occurs to me, it's funny, it hadn't occurred to me until this talk, about looking for life as we don't know it almost requires looking first for habitability as we don't know it. So there's so many different habitats on Earth spanning both space and time that are extremely different over the course of Earth's history. Earth was a different planet, a couple billion years ago, and yet we still had life. So I'm starting to struggle with the idea even of what life as we don't know it would even, where would you find it? Because basically we're so constrained or maybe even trained on the idea of habitability first and then life. So I don't really know how to make this a question other than, to me, there is a question about how you look for habitability as we don't know it.
Yeah, amazing point. Totally agree. And it does tie into the whole moon thing. Like, why can't the moon be a habitable environment for some alien type of life?
Yeah.
For sure. I think the answer is we just need a lot more researchers on this to really try and start nutting out more about it. Yeah.
Yeah, the moon is actually a fun concept here now with habitability as we don't know it. I mean, it seems like an uninhabitable place, but maybe it isn't.
Isn't one of the requirements for life that you have a solute, that you can, because you're transferring energy, you talked about redox gradients in other words, so habitability in some way would necessitate a lubricant or whatever that is.
Sometimes,
yeah. Whether it's methane or water or sulfur, liquid sulfur or something. I know that people have spoken about that before. Yeah,
something other than water, ammonia or something like that. If you think that life could exist without water, or a different biochemistry like silicon, that's where you start to go in.
Yeah.
Just on that point, there's been a word thrown around by like Dave Deemer and Bruce Damer about urability, and Laurie Barr just put a paper out about this as well, and it's basically the biosignatures of a origin of life environment. So a good example is that you look at the International Space Station, you can have tardigrades living on the outside of that, and that's technically habitable for that life. The life wouldn't have formed there. It's not an origin of life site.
Yeah.
And like Albert Martin and I have been talking about what kind of geochemistry is affected by origin of life chemistry, and looking at that. Is there you talk about agnostic biosignatures, can you go one step further and look at agnostic biosignatures for origin of life systems? Is that something that
yeah, that's for sure. That's something, and to be honest, the Laboratory for Agnostic Biosignatures team is so diverse that I was struggling to get my head around what everyone's doing. So it's possible that a team's actually looking at that from that angle already. But yeah, it's like Martin said, this is really a new developing subfield of life detection, searching for life. So might convert you.
You have to change your terminology though. You can't talk about biosignatures for
yeah. We need to come up with new words, really.
Yeah.
Almost.
What was the word you had?
So I think so they've got this paper that like urability or urability, and like it's ur is like Latin for forming or life.
Right.
Yeah, and it's kind of like not the habitability, but it's like the ability for life to form there.
And this really comes out of the idea that this whole idea of follow the water, looking for life, is all about when life already exists. But what were the conditions required to get life started? Which is exactly what this three-body chemistry about, and why hot springs or wherever is of interest. But those conditions may not be what you need for habitable or extant life. So yeah, we get down to complexity. Really. So that's definitely an aspect. Yeah.
I got a complexity question. So first of all, thanks for the nice talk. And I was wondering if you knew, or if anybody on the team is working towards trying to find sort of false positives for this MA theory, trying to look for abiotic processes that can generate similar types of distribution curves.
I assume that is part of what they're doing. Yeah. And I know it's ongoing work. This was just the recent, first stage paper on it. So actually, there's two now. There was a kind of pre one, and then this is more developed. So yeah, it's.
Yeah, because it's almost like as a goal of prebiotic chemistry, maybe we should be trying to generate those systems that can reproduce those curves. Maybe there's some out there that could lead productively towards this eventual path of getting to a protozoa.
Yeah.
I mean, there are groups that are looking at organic molecules in space and how complex they get, of course.
Yeah.
But that might be interesting. The thought might kind of occur, I'm sure, would stay relatively limited.
Yeah.
Anybody else?
Speaking purely hypothetically, how hard would it be to get some of those moon rocks?
Purely
Heaps of them. Didn't they brought back, Apollo brought back heaps of rocks?
Yeah, didn't they bring back like 700 kilograms of them or something? It was some ridiculous amount.
You can buy some online.
What?
Yeah, go on Etsy.
That's an extremely ballsy thing to do. I love it.
What was that?
He was
Some NASA tech stole a piece of moon rock to put under his bed, so he metaphorically stepped on the moon.
okay. Tell me if you had the opportunity to steal moon rocks, you wouldn't do it because
So, no,
I would.
No, but seriously, like, I was asked to to a meeting in celebration of the emergence of a meteorite, and there was a guy there who had sliced up pieces of moon.
Yeah.
So, now, I didn't have the oxygen isotopes to determine definitely that there were moon rocks, but I think they are probably.
So again, purely hypothetically, you could get some.
It appears possible. Yeah. But of course, they're contaminated now, so the only time they're